Here in 9.3, we are going to be testing the difference between means. You're going to see similar things from 8.3. We'll just be looking at differences. The objectives here is to perform a hypothesis test for claims about a difference between population means where the samples are dependent, such as with matched pair designs. And you'll be able to interpret your results in the context using common language. Let's begin by looking at the weight loss example. We have the manufacturer of an appetite suppressant claims that when the product is taken as directed with regular exercise for 4 months, the average weight loss is 20 pounds. How would we test this claim? What type of study would be best, and how would the study be designed? So we would test this by comparing the two using hypothesis testing. And the type of study that would be best would be an experiment where we need a treatment group and a control group, and we could do a matched pairs design. So matched pairs as dependent samples. In Chapter 1, we discussed matched pairs as a way to design an experiment. Observations are paired, one treatment and one control, to some common identifying factor. Some examples would be things like twin studies, data categorized by time, like year, or before and after studies. In matched pair designs, the observations in the treatment and the control group are not independent of each other. So here, looking back at the weight loss data, again, we have the manufacturer of an appetite suppressant claim that when the product is taken as directed with regular exercise for 4 months, the average weight loss is 20 pounds. Our table is showing the weights of 12 randomly selected individuals who use the suppressant as directed. So what we're going to look for is this data consistent with what the manufacturer claims? A t-test for the difference between means. So we use t-test in 8.3, so we are going to be using t-test again. So here, if you take that data from the previous slide and you find the mean of the differences, you get 17 pounds. So is this data contradictory enough from what the manufacturer said that we can reject the claim? So our big question here is, if the true difference is on average 20 pounds, would we be surprised to get to these results where the mean is 17 pounds? We will use a hypothesis test called a t-test to answer this question. Our requirements here are going to be that the data are from dependent samples like matched pairs. The matched pairs themselves are from random sample, and the central limit theorem must hold for the pairs. So remember, that is either that there's more than 30 pairs or the population of differences is approximately normal. So some new notation for 9.3. D is going to be the difference between the two data values in one pair. U sub D will be the mean of all the differences, D, for the entire population. D bar will be the mean of the differences in the paired sample data. S sub D will be the standard deviation of the differences, D, for the sample pair data, and N, the number of pairs in the sample. So our steps here is going to be the first thing that you have to do, and you can see it labeled here as 0, because the other steps actually are not changing. The other steps are not changing, but we're just adding one to the beginning to define how we are subtracting D. So you can say, let D be X sub before or X sub after. Another way you could write it would be, let D be X sub treatment minus X sub control. You can write it either way. Just make sure that you do tell me how you are doing the subtraction. It does not matter what order you subtract. You just must always be consistent. So then our first step, of course, after making the order of subtraction is going to be writing your pair of hypothesis, label the claim, identify or specify the level of significance, draw a graph of the sampling distribution and tell if it is two-tailed, left-tailed, or right-tailed, calculate the test statistic. So again, this is going to be a t-test. So you're going to be using your t formula. You'll be doing d bar minus u sub d over s sub d over the square root of n. Then you find your p-value. Remember, for a right-tailed test, you're going to use t.dist.rt. For a left-tailed test, you're going to do t.dist. And for a two-tailed test, you will use, if it is a negative test statistic, you'll do your left tail. If it's a positive test statistic, you'll do the right tail test, and then make sure you always double the area that you calculate. You will finish by making your decision about the null hypothesis by either rejecting the null hypothesis or fail to reject the null hypothesis. Make that decision by comparing your p-value to your alpha. If you guys notice, this has not changed throughout Unit 3. And then you're going to write your interpretation using common language in terms of the original claim. Again, interpretations have not changed from the way that we've written them throughout the entire semester. Here's the same table that you've seen multiple times now. And then just remember that you must include the level of significance and then the decision in terms of the claim, either based on the data or evidence. Okay, so looking back at our weight loss example, we know that the manufacturer is claiming that when regular exercise for 4 months and this product is taken, the average weight loss is 20 pounds. We have our table. We're going to test the claim at an alpha of 0.05. We're assuming that the differences are approximately normal, and we are going to put this data into Excel. I'm going to go through this without Excel here, and then I'll have to also make a video of using Excel so that we can find our D bar and S sub D. So the first thing that we're going to do is to find D. So this time, let's let D be X sub original minus X sub after. So if the manufacturer is correct, will D be positive or negative? So what I want you to think about is if this is the original weight column, and we're saying after they should weigh less. This value over here should be less than the original. So the next thing you need to think about is, well, what would this be, positive or negative, when you do this subtraction? So if the original value is large number and the weight loss then should be a smaller number, and we're doing original minus after, a large number minus small number is a positive value. Now we're going to write our hypothesis. So we're going to write this as mu sub D equals 20, and this is their claim. Okay, so why is it equal to 20? Because we're saying the average weight loss is 20 pounds. So then that means mu sub D not equal to 20 is our alternative hypothesis. Always write our alpha in. We're testing this at an alpha of 0.05. And our sampling distribution, of course, is a normal curve. And because the alternative is and not equals to, this is a two-tailed test. Now, if we put this data into Excel, again, I'm going to create another video to show you guys all of those steps. Then I am going to get some information. So D bar is going to be 17, and the standard deviation is 2.13. You will be using equals average and stdev.s to find this information. Mu sub D comes from our hypothesis, and n is 12. Now you can fill in your test statistic. So 17 minus 20 over 2.13 over the square root of 12. If you put that in Excel, you get approximately negative 4.88. Now you're going to use the test statistic that you found of negative 4.88 and figure out what the t-value is, or sorry, the p-value. This is a two-tailed test and the test statistic is negative. So we're going to use t, again, test statistic is negative. We're going to use t.dist to do this. So we're going to put in our test statistic of negative 4.88 and then our degrees of freedom true, and this would give us approximately 0.00024. And because this is a two-tailed test, make sure that you double it. So you're going to just do times 2, and that's going to give you a p-value of 0.00048. We're going to compare 0.00048 to 0.05, and we know that that value is less than 0.05, so we reject the null hypothesis. You would use your interpretation table and write this as at a significance level 0.05, there is sufficient evidence to reject the manufacturer's claim that the average weight loss while using supplement is 20 pounds. Let's look at another example. We have jump heights. A shoemaker claims that athletes can increase their vertical jump height using a new Leap brand shoe. The vertical jump heights of 8 randomly selected athletes are measured in inches. After the athletes have used the Leap shoes for 6 weeks, their jump heights are measured again. Assume that the difference are normally distributed, and we're looking at is there enough evidence to support the shoemaker's claim at a significance level of 0.01. So here we have our old height, which means before using the shoes, and our new height is going to be after using the shoes. So what we're expecting is an increase from old height to new height. So we know that the shoemaker is claiming that athletes can increase their vertical jump height using their new Leap brand shoes. So we need to figure out, how do we define the differences? If we say that D is X sub old minus X sub new, then I want you to think about, will mu sub D be positive or negative? If you're doing old minus new, then that would be what they're claiming is how you have to think about it, is the old number should be small and the new number should be larger. So if I do small minus large, I'm going to get a negative value. That's why you see mu sub D less than 0, okay? This value would be negative. If we were to say the new minus the old, okay, so then that would be a large minus a small, that would be a positive value. That's why you see here mu sub D is greater than 0. So it does depend on how you write this. You would end up with the same answers in the end. You just need to make sure that you write them the right way. So let's go ahead and write our hypothesis. So our D is going to be X sub new minus X sub old. Again, remember this means that it's going to be a smaller value minus a larger to give me a negative. So then that means my null hypothesis should be mu sub D is less than or equal to 0, and my alternative hypothesis is mu sub D is less than 0. This is our claim. Because there is a change. They don't want it to be equal. They want to see that they are getting a negative value here. So let's go ahead and write our alpha here is 0.01, and our sampling distribution is going to be a left-tailed test. I have used Excel to find all of this information. So mu sub d equals 0. That's coming from our hypothesis. D bar is our mean, so negative 1.75. S sub d is the standard deviation of the differences, and that is 2.12, and n is 8. Now I'm going to use that information for my test statistics, so t equals negative 1.75 minus 0 over 2.12 over the square root of 8. And if you put that in Excel, you get approximately negative 2.33. I'm then going to use that test statistic to find my p-value. And because this is a left-tailed test, I'm just going to use t dot dist, negative 2.337, true, and that gives me 0.026. Make your decision, so compare your p-value to your alpha, and 0.026 is greater than 0.01, so we're going to fail to reject the null hypothesis, and then of course write your interpretation. Here is the interpretation. At alpha equals 0.01, there is not enough evidence to support the shoemaker's claim that the athletes increase their vertical jump height by using leap shoes. So, does it matter which order we subtract? No, you just must be consistent. So ask yourself the question, if I subtract in this order and the claim is true, will the differences be positive or negative? And then write your hypothesis that way and double check your calculations in Excel. So what if we defined x sub d as x sub nu minus x sub o in this shoe example? What would change? So looking at the reverse subtraction, this then would be d is x sub nu minus x sub old. So this would be, the new should be a larger value than the smaller old value, and large minus small is positive. That means that we're looking at mu sub d is greater than 0 this time. And this is our alternative hypothesis. So our null hypothesis is mu sub d less than or equal to 0. Alpha 0.01. This will be a right-tailed test because it's greater than. And then, again from Excel, I would find mu sub d is equal to 0. Our average of the differences is 1.75. Our standard deviation of the differences is 2.12, and n is still 8. Our test statistic here is going to be 1.75 minus 0 over 2.12 over the square root of 8, and if you put that in Excel, you get approximately 2.33. Our p-value here, because it's a right-tailed test, you'll do t dot dist dot rt, 2.337, and this is going to give us 0.026. Compare your p-value to alpha. So 0.026 is greater than 0.01. Fail to reject the null hypothesis. Our interpretation is going to be the same as before. So what changed here? The direction of the symbols, in our hypothesis, the direction of the test, the sign of the test statistic. So I'm going to put the t and our p-value formula. that was the changes we saw, but we ended up at the same answer. So that completes our Unit 3 with the differences of means, and your lab manual pages here, 88 to 92.